All right, we're starting into our new chapter today. It's chapter 7, called Cartesian Vectors. So what we managed to do so far through chapter 6 was just talk about vectors in general and what vectors could be used for, what they required, the direction and magnitude idea. And you remember right at the end of chapter 6, we looked at changing vectors into horizontal and vertical components. Well, that's what chapter 7 is all about. It's the idea of trying to use vectors mostly on a grid. So if we put them on a grid, how are we able to make use of a vector that way? So we'll basically just get right into it, I suppose. Here's a vector. There's two equal vectors, I suppose, on this picture. I've got one labeled as vector OA, and it's starting at the origin, so starting at 0, 0, and it's going to the point 3, 1, which I'm calling point A. Now I want you to notice that this other vector up here, this is the same vector, because we've been saying all along the location of a vector isn't important. What's important is the direction and the magnitude. So that vector there is the same. But for our purposes, it's going to be a little bit easier to think about a vector as if it was starting from the origin. If we imagine it starting from the origin, then we can think of it in terms of points. So point 3, 1 is the head of vector OA. And so what we're able to do is we're going to write vector OA as 3, 1. Now the difference is I'm not using round brackets anymore because I'm not talking about a point. I'm going to use square brackets. So square brackets are indicating a vector. And the 3 and the 1 aren't called coordinates anymore. Coordinates would be for a point. The 3 and the 1 are now called components. So vector OA has components 3, 1. And officially we're calling vector OA a position vector. A position vector is a vector simply that has its tail at the origin. But for the most part, that's what we're going to be thinking of anyway. Keep in mind, that's a description of how the vector is moving. It's not a description necessarily of where it is. Okay, so vector OA is a movement in the direction go 3 to the right and go up 1. Okay, wherever I put this vector, 3 to the right and up 1 describes it properly. That's kind of a slope idea, right? Rise over run, we'd have up 1 over 3. So it's a similar idea to that. One thing you can start thinking about is eventually, well, in a relatively short amount of time actually, we need to move this into 3 dimensions. So is this going to be helpful for going into 3 dimensions? The other thing to notice here is I'm describing this vector just in terms of numbers. And in the last chapter, we said a vector needed to be two parts. It had to be a vector, or to be a vector, it had to have a magnitude and a direction. And if I'm not really giving you either of those, right? I'm just giving you a number and I'm saying go this way, go to the point 3, 1. What we have to remember is by doing that, I'm sort of intrinsically including a direction and a magnitude. If that length is 3 and that length is 1, you could get the magnitude of that vector by doing Pythagorean theorem. We're going to do that in a minute. Okay, so there is a magnitude associated with it. The other thing that's kind of associated with it is an angle. If I call that angle theta in there, you could find theta by doing a tan inverse ratio. So there's angles and there's magnitudes built in. They're just not given directly this way. So we're giving a different set of information, but that'll include the information we would need to define a vector. Here's the reason it's nice. When we were adding vectors before, we had to be really careful to add them head to tail. That's still important. We still need to do that. But then we ended up doing a lot of work with sine law and cosine law and a lot of trigonometry to come up with the sum of a vector. Let's try this one. It says consider vector A, which is 2, 1. So there's vector A right there. And vector B is 1 minus 3. So it looks like that. There's our two vectors. And if I want to add them up, what we had to do is we had to align them head to tail. So I'll pick up vector B and slide it over to there. And now they are aligned head to tail. And the resultant should be from the tail of the first to the head of the second. So that there is vector A plus B. And if we were going to write that in component form, what would that be? Well, we've started at 0, 0, so that's good. That's what we needed. And we've ended at the point 3 minus 2. And I didn't use any directions. I didn't use any magnitudes there, but I can see where it's ended up. What I'm wondering is, should we have known that from what we were given? Vector A was 2, 1. And vector B was 1 minus 3. And I think you probably noticed it there. If I just add those components up, the 2 and the 1 gives us a 3, and 1 plus negative 3 gives us negative 2. So to get the resultant, all I had to do was add the components together. And this is why Cartesian vectors are going to be really, really helpful for us, because adding vectors, subtracting vectors, doing scalar multiplication of vectors is really simple now. We don't even, well, you didn't even need the picture, right? If I had just given you those numbers, we didn't need to sketch those. We could have just added them up and got it that way. So the calculations for us, at least for adding and subtracting and scalar multiplication, are much simpler. It's also going to allow us to do a few other types of calculations, which we'll deal with later on in this unit. So here's our official definitions. It says let vector A be x1, y1, so an x component and a y component. Again, notice the square brackets. Vector B is x2, y2, so x component of the second vector and y component of the second vector. And k is any scalar, so just some real number. If I want to find vector A plus B, we just add the x components together and add the y components together. That's what we just did in the last example. The same thing works for subtraction. We would just subtract them. I guess you have to be a little bit more careful with the subtraction because you have to do it in the right order. It was vector A take away vector B. And if we're doing scalar multiplication, you just multiply through the bracket. So basically you would have had this k times x1, y1, which is just, oops, k x1, k y1. Just scaling the vector up a little bit. Okay, so that's the official definition of how our first three operations will work with vectors, Cartesian vectors. A couple of examples, let's give these a try. We have vector p and vector q. And this time I don't want to put them onto a grid, right? I just want to add them up. So p plus q, 5 minus 6, plus minus 4, 9. And I'm just adding the components together. So the first one is 5 plus negative 4, and then minus 6 plus 9. So I end up with a 1, 3. This one's a little bit harder to be just a little bit more careful with it. This is saying take 3 vector p's and subtract 5 vector q's. So 3 vector p's would look like this. The reason I picked this example, we have to be a little bit careful with how we handle that subtraction at the end. The first one's not too hard, right? We're just going to multiply the 3 in, so we'll have a 15 and a minus 18. The second one's trickier. There's two ways to do it. You can either multiply just the 5 in, which I'll show you here first, or you could multiply both the negative in. I'll show you that second. They both work. It just depends on how you think of it. You have to be careful. So I'm going to leave the minus sign, okay? So I'm multiplying that new vector by just positive 5. So the minus sign stayed, okay? I'm going to multiply everything by positive 5, so minus 20, and then 45 in the bracket. And so now when I put these vectors together, I'm subtracting them. So it'd be 15, take away minus 20. So that would become an addition, 35. And what's this, minus 18, take away 45 more is minus 63, I think. Okay, that's one way to do it. Now I'm going to, well, let's see, I guess I can just jump down here. This is my OR. This is the other way I could have done it. Same thing for the first vector. There's nothing we can do differently there. I'm still multiplying the 3 in. but this time I'm going to multiply both the 5 and the minus in. Now, because I'm multiplying the negative sign in as well, now it becomes that I'm adding the second vector. So now we have a plus 20.
Mr. Ryan,
here,
contact the office, please. Mr. Ryan, contact the office.
And a minus 45 there. And it doesn't change the answer at all, right? But the signs have just moved to different places. So we end up with a 35 and a minus 63 still. Same answer no matter how you do it. It just depends on how you think it. Right. I told you this was coming. Can we figure out the magnitude of vector p? So vector p would look, well, let's do a little sketch. I'm going to get rid of some stuff here just so we have more space. Okay. Oops, I lost my vector. Magnitude of vector p. So vector p looks more or less like this. 5 minus 6, it's coming down here like that. So 5 over and down 6. Well, what I've created really is a triangle, right? I draw that line in. I've got a little right angle triangle. And the fact that it's minus 6 is just there because it's going down, right? But I don't want to think of it as minus 6. I'm just going to think of it as a positive 6 for a minute. That's simply the distance. So that gives me a right angle triangle. And I'm trying to figure out that magnitude right there, how long that vector is. So using Pythagorean theorem, the magnitude of that vector is 5 squared plus 6 squared. And so to actually get the magnitude, I'll take the square root of 61. And we can just leave it like that, right? Square root of 61 is an exact answer. That works out really well. Now, one of the nice parts, this worked well from a geometric standpoint. You can see the 5 and you can see the 6. Notice if I had left the minus 6 and I'd subbed in minus 6 into the Pythagorean theorem, which seems kind of weird, right? Pythagorean theorem, we usually sub in lengths. But if I sub in minus 6 there, it doesn't change anything because minus 6 squared is still 36. So it didn't even matter. So often when you see the formula, which I think you'll see on the next slide, it's not going to talk about changing the sign or anything. We just sub in whatever it is. And when we square it, we get the positive version of the answer anyway, which is what we want. Okay, D is another large one, so let me get this out of the way again. Here's D. Determine the angle between P and Q. And in brackets there I said always if joined tail to tail. What I mean by that is whenever we talk about the angle between vectors, we are always assuming that they're tail to tail. And that's an important one. That's going to come up for us a few times in this course. So if we're talking about the angle between vectors, we're assuming that they're aligned tail to tail. So I need the vectors on here. 5 minus 6 for vector P, we just had, right? That was more or less here. 5 and minus 6. And then vector Q is at minus 4, 9, so it's a little steeper. Something like that. And we're trying to find, change colors here, we're trying to find that angle all the way. What's the angle in between vector P and vector Q? We're going to look at a few different ways to do that throughout this unit, but there's one way we can do it right now. It won't be the fastest way as it turns out, but it's for what we know at the moment, it works out pretty well. What we want to do, if we're trying to find that big green angle, we're going to break it into 3 parts. So I'm going to find angle alpha up here. This has got to be a 90. And then I'm going to find angle beta down there. And if I add up alpha, beta, and the 90, that should give me my overall angle. So that's what we're going to try. I'm going to do the same trick we did in the last one, thinking about right angle triangles. for the triangle on the top, I'm going to draw that line across. We have lengths of 9 and 4. So for angle alpha, 4 is the opposite and 9 is the adjacent. So if I do tan alpha, it'd be 4 over 9. And then if I do a tan inverse of that, that gives us about 24 degrees. There's a decimal there, but it's pretty close to 24. And then same trick for beta. I'm going to drop that line down too, so I have another right angle triangle. Now I've got a 6 over here. So the opposite of beta is a 6. The adjacent is the 5. So tan is opposite over adjacent. And again, we'll do a little tan inverse. And this time I get about 50 degrees. So overall then, the total angle is, what was it, 24 plus 90 plus 50, and what's that, 164 degrees is our final answer. Not the only way to do that question. As I say, but by the time we finish this unit, there's probably about 4 different ways that we could have made that calculation. But that's not a bad one. Right? It helped to draw the picture. We needed to draw the picture. And then think a little bit about right angle triangles, and we can get it that way. Okay. Next example says, given the points P, 3, 5, and Q, 6, 8, determine vector PQ, and then determine the magnitude of it. And then we're going to get a little in general formula there in a second. So here's a little sketch of what this should look like. Not to scale, but I'll come close. Point P is at 3, 5, so around there. And point Q, notice these are points, right? These had round brackets. So point P and point Q, about there. And we want vector PQ. So start at vector P and go to vector Q. So the first part was just, can we figure out what that vector is? And there are 2 different ways you can think about this, and they both work just as well. One way is you go to the point, which was the head vector. So Q was the head vector, or excuse me, the head point, and you subtract the tail. So vector PQ would be the 6 there, take away the 3, which is 3. Okay, I just did 6, take away 3. And then the second one, you go 8, take away 5. And that works really well. Okay, we can get the point that way. The other way to think of it, erase this for a minute, and quite honestly, I do a bit of both of these, depending on the situation I'm in. This is the way I like it, though, I suppose. I think of it in terms of, okay, what do I need to go from P to Q? So if I want to go from a 3 to a 6, what I needed to do was add 3. So I put that plus 3 there for the x component. And then for the next one, I needed to go from a 5 to an 8. And what did I need to do that? Well, I needed to add 3 again as well. Just a coincidence that they were both 3s. But that's how I tend to think of it. Okay, and now we should be okay getting the magnitude of that. We just finished seeing that Pythagorean theorem would work, right? So the magnitude of vector PQ squared is equal to the sum of the squares of the components. So 3 squared plus 3 squared. And what is that? 9, 9, 18. And then I'll take the square root of that. And this is a good little review example for us. Square root of 18 can be reduced. It doesn't turn out to be a perfect integer, but this is one of the ones where we can write like that. Square root of 9 times square root of 2. Square root of 9 is just 3, and the root 2 we leave. Okay? So it's not a bad way of being able to simplify it. Okay, I need to slide that out of the way so we can get the in general stuff up. Everything that I'm about to slide out is just well, it's exactly the same as what we just did, except instead of having points 3, 5, and 6, 8, I'm just going to call them points x1, y1, and x2, y2. Sort of look like this. So if we have points x1, y1, and another point x2, y2, then the way we find a vector, and this is how we have to write it from a formula perspective, was the first way I explained it. Take the point that was the head and subtract away the point that was the tail. So x2 should be there. Take away x1. And then y2 take away y1. Right, that will work. And then to get the magnitude, we're just using Pythagorean theorem. And that's all that's happening here is using Pythagorean theorem. We're taking the components, squaring them, adding them up, and we took the square root. Two nice little Cartesian vectors that we are going to use a fair bit are called I and j. Well, fair, we'll use them occasionally. These are the simplest vectors that we can possibly have. So vector I is just 1, 0. So all it does is it goes right 1 unit. There's vector I right there. That's all it does. The magnitude is 1. It's going right 1, it's not going up or down at all. So it has a magnitude of 1, goes directly to the right. Vector j goes up 1. So it also has a magnitude of 1. We sometimes call those unit vectors. Any vector that has a magnitude of 1 is called a unit vector. And as I say, those are pretty straightforward little vectors, but we can use them a little bit for a question like this. This is something we talked about in the last unit. We can write any other vector in terms of two non-collinear vectors. Remember, collinear vectors were vectors that were parallel to each other in the same or opposite directions. So as long as I have non-collinear vectors, I was supposed to be able to write any other vector in terms of them. Well, I and j are certainly not collinear, right? One's pointing to the right, one's pointing up. So what I want to do is I want to write vector u, which is minus 26, 14, so some random vector. Can I write vector u in terms of i's and j's? So I need some number of vector i's plus some number of vector j's. And this is not supposed to be a hard question here. I and j are the simplest vectors we can possibly pick. So for vector u, if I want to go, well, I need an x component of minus 26. That means I needed to go left 26, right? Vector I goes right 1. So I need to change the direction, but I need 26 of them. So I just put a minus 26i there. And vector u needed to go up 14. Well, vector j goes up 1. So I just need 14 vector j's. So that's one way that I can use I and j. Not an exciting example, but it's something that we can do with them. Now we have one more example where basically we're going to try and do the same thing. I'm giving you two new vectors, a and b, not nearly as helpful as I and j were. And what we want to do is write vector u as a linear combination of a and b. So same thing we did before with the I and j. Can I write this? Can I write vector u equals some number times vector a plus some number times vector b? And we did this before in the last unit. I'm not sure if you remember, we had that great big grid and we were trying to come up with a way of writing one vector in terms of others. It becomes a little bit easier to see it now that we have Cartesian vectors. We're able to write it in a slightly simpler way. So for example, I can already substitute here. Vector u is minus 26, 14. And that's going to be some number times vector a, which is 2 minus 5, plus some other number times minus 3 minus 1. Now, technically we have two variables, right? We have m and n, and we're trying to figure out both of them. It kind of looks like we just have one equation, but we really don't. We have two. We have an x component equation, and we have a y component equation. So here's equation number one. Just if I'm pulling out the x components, okay? So the x components are the minus 26, the 2, and the minus 3. Now I have to keep in mind the m and the n are there too. So minus 26 is equal to 2 times that m value, so 2m, and then minus 3 times the n value. And then for the second equation, now I'm going to look at the y components. So for the y components, I have 14 is equal to minus 5m's minus 1n. So what was one equation, we've turned into two. This is now a linear system, a grade 10 question, right? We can solve these by either substitution or elimination. And either one works. Elimination is my favorite, so that's what I'm going to do. I'm going to look at trying to eliminate either the m's or the n's, and it looks like the n's are going to be easier this time because this one on the bottom has a coefficient of 1. So I'm going to multiply this bottom equation by 3. Top equation I can leave. So this is still minus 26 equals 2m minus 3n. It's the bottom one that changes. 14 times 3 is 42. Minus 15m minus 3n. So we've managed to get the coefficients in front of the n's the same. And so in order to eliminate them, I need to subtract. Always have to be more careful with subtracting, just so we don't make any mistakes. Minus 26 take away 42 is minus 68. And then 2 take away minus 15 would be 17m. And the n's should disappear, right? Minus 3 take away minus 3 would be a 0. So the n's are gone. And that works out nicely, actually. Minus 68 equals 17m. Divide both sides by 17, and you get minus 4 for m. So that means that I need minus 4 vector a's. Right? That's what we have so far. We're not quite done. We still need to figure out what n should be. So we are going to, let's see, can I get a little more space here? A little bit. I'm going to slide this down and this. I'm going to substitute the minus 4 in for m. That'll be a positive 20, so subtract 20 on both sides. So minus 6 equals minus n. So n equals 6. And now I can get my overall statement then. I've got therefore vector u required minus 4 vector a's, and it required 6 vector b's. So we were able to solve that system that way. And you could check that if you wanted to, right? You could actually multiply vector a by minus 4 and multiply vector b by 6 and put all the components together and make sure you really did get minus 26, 14. But this worked. Keep in mind, this worked out relatively nice because we got the minus 4 and the 6, which are pretty good numbers. This should have worked no matter what vector u was. So if I picked any two random numbers for vector u, we should have been able to solve this. All that would have changed is those two numbers right there would have been different. But the way we would have solved everything was the same. In fact, we still would have multiplied by minus 3, right? We would have ended up getting a different number here, and then in turn a different number there, but it still should have worked, right? So what we're saying is that no matter what vector I want, as long as I've started with two vectors that aren't collinear, remember, vector A and vector B were not collinear, they were in different directions, then we should be able to write any other vector in terms of the sum of those two. And there you go, that wraps up our first chapter, or our first lesson, I should say, in chapter 7.